this computer. Okay. All right, so let's see. I need to share my screen. So just give me a second to make this work. Da, 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 da. Da, da. Okay, so can everyone see the whiteboard? Wait, let me get my chat up here. Let's see here. Chat. Okay. So this is visible. So we're going to look at section 12.1, three-dimensional coordinate systems. And please unmute yourself and ask a question if something's not clear, if you can't read my writing, and so forth as we're going along. Or you can ask a question on chat, but not always going to see the chat question immediately. All right, so in 243, we cover section chapter 12, chapter 13, chapter 14, chapter 15, chapter 16 of your textbook. 12.1 sort of develops a bunch of preliminaries that we're going to use later. There's not so much calculus in chapter 12. And 12.1 is on 3D coordinate systems. So 3D refers to three-dimensional. And what that means is that three numbers are used to identify or label a point in space, or 3D space if we want to be specific. All right, so this should not be a new idea, right? If you remember the number line, you put numbers along a line like this, and if I give you the number square root of 2, say, that identifies a point on the line. If I give you a point on the line, there's going to be a number that goes along with that. So there's a one-to-one correspondence between a set of, in this case, one number and a location, okay, a point on the line. So this is an example of a 1D coordinate system. Okay, and you all have seen 2D coordinate systems as well. Typically, we can think of things in terms of the Cartesian plane. So we have two axes at right angles to each other. Typically, we label the horizontal axis X, the vertical axis Y. And if we talk about a point in the plane, we can label that point by a pair of points. So there's a question in Canvas. Will the notes be uploaded to Canvas or somewhere else where we can see them later? And the answer is, I will try to do that. You do have a textbook, so please make use of the textbook. I will type up some of the notes. I can't guarantee that all of the notes will be typed up, but I'll try to type up most of the notes and make these accessible to you. Okay. So 2D coordinate system, an ordered pair of numbers. That first number is telling you an X location. The second number is telling you a Y location. So the way you want to think about this is you go, whatever that first number is, that gives you a location on your X-axis. Whatever the second number is gives you a number on your Y-axis. And then you look for the intersection of the vertical, the perpendiculars to the axes corresponding to those two numbers, right? The intersection is going to give you your point. So you can think of what you're doing as if I give you, let's say 1, 3, that means go 1 unit out along the X-axis and then 3 units in the positive direction along the Y direction, and that gets you to your point. Okay, and in 3D, the idea is exactly the same. I can't draw this easily on a 2-dimensional picture. Before we get there, there's one sort of subtle point that maybe you haven't thought about. With each number line, there's a positive direction that goes along with it. So I could have put my X and my Y axes together in 2 ways. If the X axis is labeled like this, and the Y axis is labeled like this, right? There's a positive direction and a negative direction for each axis. And this is sort of the standard way to put the 2 axes together to come up with a labeling scheme for the plane. You could, in principle, make, instead of up the positive Y direction, you could make down the positive Y direction. And there's no particular reason that one of these is better than the other. It's tradition, or it's a standard convention that this is the way we orient the axes, and we use our coordinate system corresponding to this orientation of the axes for the 2D plane. Okay. Now, in the same way, with a 3D coordinate system, right, we can use so-called rectangular or Cartesian coordinates. We're going to have 3 axes. Okay, so you sort of have to think, you have to use perspective to try to interpret what this picture is saying. So we're going to think of the positive X direction, positive Y direction, positive Z direction, where the 3 coordinate axes mutually intersect is the origin. Okay, and we want our X and Y axes to be consistent with the orientation that we use when we're dealing with the plane. So think of the XY plane. And then the Z axis, we have sort of two choices for what the positive Z direction is going to be with relation to the X and Y coordinates that we've picked. So what I've drawn is the standard convention, and this follows what's called the right-hand rule. Okay, so think of taking your hand, your right hand, point your fingers in the positive X direction, curl them towards the positive Y direction, and your thumb is going to be pointing in the positive z direction. So x, y, z are the first, second, and third coordinates or components of your label for points in three-dimensional space. And you have to follow the right-hand rule to see how these axes are related to each other, at least the standard convention for how the axes are related to each other. Right, so you should always remember that. Now, we will see later in the course that there are other 3D coordinate systems. There are, in fact, about 10 different 3D coordinate systems that are commonly used. And of these, there are 3 that are most commonly used. The others are sort of not things that you will have to worry about in Math243. You will, however, see spherical coordinates, and you will see cylindrical coordinates. Okay. In the 2D setting, we have our rectangular coordinate system that we've seen. We also have polar coordinates, which you may have seen before. For instance, I know their polar coordinates are discussed in Math242. So we'll worry about spherical and cylindrical when we get to them. For now, we're going to think about rectangular 3D coordinate systems. And there's some terminology that goes along with these. So there are the coordinate planes. So in three-dimensional space, you can embed two-dimensional planes in lots of different ways. The plane that contains the x and y axes is the xy plane, or the xy coordinate plane. There's a plane that contains the x and z axes. This is the xz plane, or the xz coordinate plane. And there's a plane that contains the yz, the y-axis and the z-axis. So that's the yz coordinate plane. Right, so you should understand what the coordinate planes are. Okay, and let me just go back to the XY system. So you may remember that there's a way of, naming the quarter planes. So the first quadrant, the first quarter plane corresponds to this region of the plane. That's the quarter plane where x and y are both positive. And then we have the second quadrant, the third quadrant down here, and then the fourth quadrant down here. If you think about embedding the 3 coordinate planes in 3 dimensions, 3-dimensional space, those will divide space up into 8 subregions. Those are called octants. Okay. And the first octant is the region corresponding to x, y, and z positive. Okay. So does that make sense, everyone? Any questions so far?
Sorry, Professor.
Yes.
I don't really know what you mean by right-hand rule.
Okay, so let me stop sharing here for a second. Okay, so my left hand, my right hand.
Yeah.
Okay, take your right hand.
Okay.
Think of your fingers pointing along the positive x-axis, right? Your fingers are pointing in the positive direction along the x-axis. If you curl your fingers towards the positive y-axis, then your thumb is going to point in the direction that you should pick for your positive z-axis. Okay, that's where the name right-hand rule is. Right-hand rule comes from. It tells you how to pick the positive z direction, giving you your positive x direction and positive y direction. Okay, and notice, so think about what we did. Notice what would happen if you use your left hand. You point in the positive x direction, you curl in the towards the positive y-axis, your thumb is going to point in exactly the opposite direction. So that left-hand rule would give you a different convention for how the axes are related to each other. There's no intrinsic reason that one of these is better than the other, but the convention is that we always use the right-hand rule. That's unless you have some special reason for doing something different, you should always assume the right-hand rule is in effect. Okay?
Okay, thank you so much.
You're welcome. All right, so let's try to share again here. Da, 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 da. Okay, so let me get this back. Okay. Okay, so one of the things that is useful to do in many circumstances is to talk about distances. So in 1D, if I have 2 points A and B on my line, the distance between these is, by convention, in this case, you take the number that corresponds to the rightmost point minus the label or the number corresponding to the left-hand point, and you get your distance. Distance by sort of convention has to be bigger than or equal to 0. Okay. And what if you had your 2 points, so distance between, that's abbreviation for between points A and B. If you don't know which is the bigger one, you can use the absolute value to get your distance. Okay, remember that this would be B minus A if B minus A is bigger than or equal to 0, or A minus B if B minus A is less than 0. So notice either way you get something that's bigger than or equal to 0. If B happens to be to the left of A, then you reverse things there. And that's essentially what we want to generalize in 2D. If we've got 2 points in the plane, we want to know this distance. We can get that by building a triangle. So if we have 2 points, x1, y1, and x2, y2, we can get the distance between these 2 points by building this triangle. And if we know that our coordinates are x1, y1, say here, and x2, y2 for this point on our triangle, we know that this bottom leg of the triangle has length absolute value of x1 minus x2. We know the vertical leg has length absolute value of y2 minus y1. So we can use the Pythagorean theorem to get the distance. Okay. And in the same way, when we have two points in three-dimensional space, say x1, y1, z1, and x2, y2, z2, the distance between these sort of follows the same pattern. And in fact, you can show that where this comes from actually is two applications of the Pythagorean theorem. So it's not mysterious. Hopefully you've seen the version of this in 2 dimensions before. And how do we generalize? We just have this extra piece now in 3 dimensions. So that's the distance formula. So next question you might worry about is, let's say you have an equation represents some set of points. What exactly is it going to represent? Well, you have to be careful. You have to always pay attention to what space are you working into. Okay, so if I just give you x equals 1, what does that represent? Well, it depends. If you're working in one-dimensional space where all you have is the x number line, x equals 1 is a point on that line. If you're working in two-dimensional space where x equals 1 could go along with any y value, right? If that's all you have, then y should be unrestricted. And in fact, x equals 1 would correspond to a line in two-dimensional space. And in three-dimensional space, x equals 1 would actually represent a plane parallel to the YZ coordinate plane, but 1 unit in front. Okay. So I'm going to try to say this precisely. Okay. So the same equation can represent different things depending on which space you're trying to work. Right, so always keep that in mind, be precise. Let's say, now let's think about in 2D, we've got our XY plane, there's a point AB, and we want to know what is an equation for the set of points which is equidistant from this point. Okay, so does anyone remember what we're talking about? The set of points equally distant from a given point. So what do we call that set of points? So it's a circle, right? And what's the equation of the circle that we're talking about here? So remember, we want the distance of an arbitrary point x comma y that lies on our circle. The distance from that point to our center point, a comma b, should always be the same. So if we compute the distance from xy to AB, we want that to be r. Well, we know what the distance formula is. And it's traditional to square both sides here. To get the equation of a circle. Okay, so do you guys remember seeing this at some point? Hopefully, it's not totally unfamiliar. Well, you can do the same thing in 3 dimensions. And you will get what's called a sphere. Okay, so if the center is A, B, C, and the distance is called the radius, say that's r. If we just use the distance formula in 3D again, we get this equation. Okay, so it looks very much like the circle. We just have this extra term. That extra term makes this a sphere. What if we just looked at the first part? Oops. Okay, can anyone work out what we're talking about here? And I have to be careful and say I want to know what is the surface in 3 dimensions.
Is it a cylinder?
That's exactly right. So can you explain your reasoning?
Because you just like make a circle and then I just kind of like pushed it in like the Z direction and it makes like a 3-dimensional like cylinder.
Yeah, that's exactly right. So I've got my center AB. I draw my circle in 2 dimensions around it. If I was working in 2D, that would be a circle, right? This would be a circle. So now in 3D, what I need to think about is I've got X, I've got Y, I've got this point that lives in my XY plane. Notice if I take my axes here and rotate to line them up with the XY axes in my 3-dimensional coordinate system, if I now add the fact that Z can be whatever for an X and a pair of XY coordinates that lives on the circle, essentially what I have now is a line perpendicular to the plane that passes through every point on the circle. And if I put those all together, and I'm only drawing a finite part of it here, right? This really continues in the positive and negative Z directions forever. That's giving me a cylinder. So again, an example where I've got an equation depending on whether I'm working in 2D or 3D, I could have that represent different surfaces. In this case, could be a cylinder. Sorry, if I'm working in 1D or 2D, this could be a circle in 2D. Sorry, I misspoke again. This could be a circle in 2D or a cylinder in 3D. Okay. All right, so what about inequalities? Well, let me ask you guys. What you think this pair of inequalities might represent. So just like inequalities in 1D or 2D, you can always figure out what's going on by looking at one of the inequalities at a time. So if you have something like x squared plus y squared plus z squared, take the square root, and it's going to be less than or equal to R1. You can square each side. Assuming both of these are positive, it's okay to square each side. And you get something like
Shouldn't it be greater than not less than?
Sorry? Oh,
Shouldn't it be greater than and not
sorry,
less?
I did it backwards. Yes, you're right. Thank you for catching that. So whenever you have an inequality and you're trying to figure out what region in your space this corresponds to, the boundary of your space corresponds to changing out your inequality but for an equality. So if I do that in this case, I get a sphere of radius R1. Okay, and you can think of x squared plus y squared plus z squared geometrically. That's the same as x minus 0 squared plus y minus 0 squared plus z minus 0 squared. So that's the distance from point xyz to the point with coordinate 0, 0, 0, which is the origin. So this is distance from the origin has to be bigger than R1. So if I think about what that means, inequality gives me a sphere of radius R1 centered at the origin. And I want everything that's further away. I want that sphere plus everything further away from the origin. So everything on or outside the sphere is what's coming from the first of these inequalities. Then from the second, I want the distance from the origin to be less than another number R2. So that's everything on or inside a sphere of radius R2, where I'm assuming R2 is bigger than R1. So really what I'm talking about here is a cylindrical shell, the region between two spheres, two concentric spheres. Okay. Is that clear to everyone? Any questions there?
You froze for a minute while you were explaining. Would you mind just explaining it again?
Okay, so when you have an inequality that represents a region, could be in whatever dimensional space you're talking about, if you want to work out the region corresponding to an inequality, you can replace it by an equality to get the boundary of the region you're talking about. And then you have to check all the regions that boundary, curve, or surface divide your space up into. For this pair of inequalities, the one on the left corresponds to a sphere of radius R1 if you replace the inequality by inequality, right? So this guy. And this guy corresponds to a sphere of radius R2. So you need the set of points that's on or outside a sphere of radius R1 and simultaneously on or inside a sphere of radius R2. So the two-dimensional analog of that would be an annulus, right? So the region between two circles. In 3D, right, you've got X, Y, and Z. That pair of inequalities corresponds to a spherical shell, the region between two spheres. Okay, does that make sense? And did you get the whole argument that time?
Yep, thank you.
Okay, very good. All right, so we're almost out of time here, so I'm going to stop sharing my Scratchpad here. All right, so any last questions before we pack it up for today? All right, so please go to the Canvas page, get the course code for the WebAssign course that goes along with our class. So let me just put it in the chat here for you. Okay, edit, paste. So there it is. Sorry, this should all go together. If you have trouble signing up on WebAssign, please send me email sooner rather than later, so we get you squared away. Okay. I will post the exam schedule soon. You don't have any exams. I think the first one will be about 4 weeks in, 3 or 4 weeks in. So I'll post it quickly. Any other questions?
I have a question. What about office hours?
All right, so for the moment, I will be available from 10 to 11:30, Monday, Wednesday, Friday. Okay.
Okay.
posted there. I may have to change this. Usually there is a little bit of fiddling with schedules that has to go on in the first week or two of the semester. So please let me know if this is going to work for you. If not, again, let me know. I'll try to put a poll up on Canvas that will let you give me some insight on office hours that are going to work for you. And also, I will put a poll up on Canvas asking what time zone you're in. So that this is an issue with some students. I think if you are in another country or just in a different region of the US, and you're in a different time zone, let me know. And we'll try to figure out office hours that will work for you. If there's a problem with exam schedules, we'll figure out how to deal with it, but you have to let me know, okay? All right, so it's a little bit past 8:50. I can hang around for another 10 minutes or so if anyone has questions. So you're not required to hang around. If you have questions, you can stay and ask.
Thank you.
Thanks. Have a good day, everyone.
Thank you.
Thank you.
You too.
Thank you.
Have a good one.
You too. Okay, everyone's gone. Okay.